This mechanics problem may give you nightmares. So imagine that we have this kraken and it's at rest. The kraken then sees a boat and begins moving towards it. After 2 seconds, the kraken is moving at a velocity of 20 meters per second. What is the average acceleration of this kraken? Whenever you need to calculate average acceleration, it's simply going to be the change in the object's velocity divided by time. So I'll start with the change in velocity. I notice in this second diagram, the kraken is moving at 20 meters per second. And initially, the kraken is at rest. So the change in velocity is 20 meters per second minus 0 meters per second. I'll then divide this by the time, which in this case the time is 2 seconds. So we have 20 minus 0 divided by 2, which should give you an average acceleration of 10 meters per second squared. So this is how fast the kraken is accelerating, and this matches with option choice D. So if you ever see this kraken, you better hope that you're either in a really fast boat or that you're close to land. This problem should be interesting. So we have our friend Baldi here from Baldi's Basics, and he takes a ruler and throws it up in the air at an initial velocity of 10 meters per second and an angle of 80 degrees. We want to calculate the peak height which the ruler will reach. To solve this problem, we can use this formula, which calculates the peak height of projectiles. We are given the initial velocity, which is 10 meters per second. We're also given the angle, which is 80 degrees. The last thing we need is g, which is the gravity constant, but the gravity constant for Earth is always the same. It's 9.8 meters per second squared, so we can plug that into the bottom of this equation. If you throw these numbers into a calculator, you should get that your peak height is approximately 4.95 meters. Now, this is not the final answer, because all this does is calculates the height assuming ground level. We need to add this 10 meter height. So the true peak height is going to be the 4.95 meters plus this 10 meter displacement, which is 14.95 meters. So 14.95 meters is the answer to the problem. This physics problem is kind of tricky. So here we have Super Mario, and we want to find his net displacement, which is basically just his change in position. Now at first, this seems impossible to calculate with what we're given, but there's nothing in physics that says we're not allowed to move these vectors around. And if I rearrange these vectors, you may notice that I can get a familiar shape to form, which is a right triangle. This leg of the triangle is 6 meters, that leg of the triangle is 5 plus 3 or 8 meters, and then all we need to do from here is use the Pythagorean theorem to recognize this is a 6, 8, 10 right triangle. So we can clearly see that Mario's net displacement is 10 meters. The Sonic problem is a bit difficult. So in this problem we have Sonic and he is moving down this road. We want to calculate Sonic's total kinetic energy. Now the reason this problem's a bit difficult is notice how Sonic has both linear motion and rotational motion. So to find Sonic's total kinetic energy, we're going to need to add the linear and rotational kinetic energy together. The physics equation for linear kinetic energy is 1/2 mass times velocity squared. Sonic's mass is 35 kilograms, and his linear velocity is 350 meters per second. So we have 1/2 times 35 times 350 squared, which on a calculator is approximately 2.1 million. The approximate value for the rotational kinetic energy is given to us in the problem. So we have 2.1 times 10 to the 6th plus 8.6 times 10 to the 5th. If you add these two numbers on a calculator, you should get approximately 3 million. So Sonic's total kinetic energy is about 3 million joules. In this physics problem, we have an imposter. The imposter sees themselves in a concave mirror. Will they see a real image or a virtual image? Now, to solve this problem, what you want to do is set up a ray diagram. When dealing with a concave mirror, the first ray of light is going to go from the top of the object to the mirror, and then it's going to reflect through the focal point, which is F. Now the next light ray you draw is going to go directly through the focal point and then reflect off the mirror. As can be seen from this diagram, the light rays appear to converge right here. So that is where the image is going to form. And whenever the object and the reflection appear on the same side of the mirror, you are dealing with a real image.